Welcome back, students. In this part, we're gonna learn hybridization technique, which is the intermixing of different orbitals to give the most stable orbital and which will form the chemical bond. So let's start this topic. So the next topic is hybridization, which is a technique in which the orbitals which are overlapping, now we'll see a new set of hybrid orbitals which get intermixed so that the energy is the lowest in these molecules. It's redistribution of orbitals. We'll see that. What is hybridization? If I'm gonna define it, and it will be, as I told you, that it is intermixing of different atomic orbitals, and they should be nearly equal in energy, nearly equal in energies, and they will produce the hybrid orbitals before the bond formation will take place. And the bond formation will take place only when this set of hybridized orbitals get formed, because they will be the most stable structure, and there will be minimum repulsion that we have studied in VSEPR theory, and the number of orbitals which get mixed is equal to the number of hybridized orbital which is produced. Now let's see the types of hybridization, different types of hybridization. First is your sp hybridization. Sp, here one s and one p orbitals are getting intermixed, so the number of hybrid orbitals produced is equal to 2. Structure is linear and bond angle is 180 degree. Example BeF2, like this. So see, by using the hybridization technique, we are able to predict the bond angle, the structure of the molecule. This is the way how sp hybridized orbitals get formed. One s and one p I am having, and they gives me a sp hybridized orbital. And now my bond formation takes place from this sp hybridized orbital. Next is your sp2 hybridization. sp2 hybridization. The number of hybridized orbital will be 3, because 1s and 2p orbitals are participating in this hybridization. The shape is trigonal planar, the regular shape. Bond angle is 120 degree, like BF3. BF3. Then we have sp3 hybridization, in which 4 orbitals are participating. Shape is tetrahedral, like CH4. The angle should be 109.28. But in NH3 the angle is 107.3. Why is that so? That is because of the distortion of lone pair electrons. Lone pair electrons repulsion. And that's why the bond angle decreases. And the shape becomes triangular pyramidal. There should be one A here, triangular pyramidal. Just look how sp2 and sp3 electron cloud look like. This is sp2 hybridization. 1s and 2p are getting hybridized, and they then overlap to form a bond. Similarly, we have sp3 like that. Carbon is sp3 hybridized here, and then the H atoms, they overlap to form a bond by sigma bond. This bond is sigma bond. Next is sp3 hybridization. Here The number of hybrid orbitals produced are 5. Structure is trigonal bipyramidal, and if you look at the equatorial geometry, then that will give us 120 degrees apart. It's like this way, a triangle you can assume, and above the plane and below the plane. This is the plane, they are 120 degree apart, and this is 90 degree. Axial is 90 degree axis. Example is PCL 5. sp3d2, number of hybridized orbitals 6, that is your octahedral, like SF6. And due to lone pairs, the geometry may distort and the shape may be square pyramidal or square planar, like XZF4, BRF5. sp3d3, number of hybridized orbital are 3 plus 3 plus 1, 7. Arrangement is pentagonal pyramidal, bipyramidal. These are the electron cloud or 3D geometry. sp3d3, the example is IF7. Hybridization technique, hybrid orbitals. Hybridization is the intermixing of nearly equal energy orbitals. When they intermix and form a new set of hybrid orbitals first, and then the bond can be easily formed because they are now stable. See here, 1s and 1p, they got hybridized and form a sp hybridized orbital, and the shape is linear, 180 degree apart. The bond angle is 180 degree. Let's see this thing in 3D. 1s and px, it combines to form sp hybridized orbital, like in beryllium chloride. There is one beryllium, electrons are in 2s. Now sometimes due to excitation there is promotion of electron from lower energy to the higher energy, that is not much more higher but nearly equal energies, and that form sp hybridized orbital, and the 2Cl atom will combine with these two sp hybridized orbital. They form a sigma bond, and so is the molecule formed of BeCl2. You have a question, pause and ponder it. Next is sp2 hybridization. Here 1s and 2p orbitals, they do take part in forming the hybridized orbital as sp2. The bond angle is 120 degree apart. Shape is trigonal planar. Let's see it in 3D geometry. 1s and 3p, 1s and 2p, when they combine, they form sp2 hybridized orbital. And now this sp2 hybridized orbital, it will give the path to other atoms to form sigma bond with them. Let's see in benzene, C6H6, what is happening in benzene? It is all the carbon atoms are sp3 hybridized, and there is 3 sigma bonds. 2 sigma bonds with the other 2 carbon and 1 sigma bond with hydrogen. And that's how formation of a pi bond also in case of benzene. There is one more question for you guys. Pause and ponder it. Now let's come to sp3. When 1s and 3p orbitals, they will combine they'll form a sp3 hybridized orbital. It will look like a tetrahedral shape. This is the shape of the molecule CH4. The bond angle is 109.5 degrees. When 1s and 3p, they distribute their energies and orbitals, they intermix to form one sp3 hybridized orbital. And the bond angle is 109.5 degrees. Let's see this thing in methane. In methane, which is CH4, the carbon is sp3 hybridized. And there is promotion of another one electron from 2s to 2p, and 4 sp3 hybridized orbitals are there, and they participate in sigma bond with hydrogen. That is how bond formation takes place through the concept of hybridization technique. Now, to find that which molecule will possess which hybridization, there are some rules. The rule says that only orbitals of approximately same energy level, they take part. Approximately same energy level they take part. The number of orbitals mixed is equal to the number of hybridized orbital produced. And this rule is very important. Hybrid orbitals only form sigma bond. And to calculate the number of hybridized orbital, you have to use the formula as NH is equal to half of V plus X minus C plus A. That means, what is my V? V is equal to number of valence electrons in the central atom. X is the number of monovalent atoms. C is the cationic charge and A is the anionic charge. When you will calculate the NH, then according to NH, if suppose you get NH value as 2, that means your 2 hybridized orbitals are participating and it is sp. If NH you are getting 3, that means sp2. If NH you are getting 4, that means sp3, like that, and you will get the shape. That's it. With the technique of hybridization, we are able to find the molecular geometric shape with the lowest possible energy and the most stable possible structure. Well students, we have covered the technique of hybridization to calculate the shape of different molecules by using the intermixing of orbitals technique.